Everyone. Welcome to this nanoelectronics course. In this course, we are going to cover different aspects of nanoelectronics. We will cover nanoelectronics from the perspective of FET-based device. Okay, we will see the detailed syllabus in a minute. Um, But as far as nano is concerned, by nano we mean that the structure of or the device is very tiny. By very tiny we mean maybe hundreds of nanometer or less. Okay, there is no hard and fast rule about the dimension, but we can. Uh, okay, yeah, you can record it. Yes. Yes, so we can. Uh, let me share my screen first. So can you see my screen?
Yes, sir.
Okay.
Yes, sir.
So by so the part we would like to cover in this course is uh, quite elaborate or in quite detail. Okay, lot of aspects. But you shouldn't be afraid by seeing the syllabus, because we will cover things very slowly, and we'll try to accommodate as much as we can. But as the course progress, you will see that our pace will be good enough to understand things. There is no hard and fast thing that we have to cover the entire syllabus, but if we can cover most of it, that will be great. Okay, so this is a 3 credit course, and the course will be, I mean, the classes will be on Monday between 8 and 10 a.m. and Tuesday, that is today, between 12 to 1. Okay, now between 12 and 1. Now so let me first show you the syllabus. Okay, uh, so we'll uh, briefly cover or briefly introduce to you about the nanoelectronics. Okay, uh, then we will move to shrinking of devices. Uh, um, you probably know, or even if you don't know in a conscious way, but the thing is, like, for example, the easiest thing to discuss is, say, electronic gadgets. Um, Many few decades ago, maybe around 1980 or before that, the computers are of size of a big room. Okay, nowadays you can keep your computer in your pocket. So so we have managed to reduce the dimension of devices. Okay, that is the shrinking of device dimensions. That is why we have managed to reduce the dimensions of electronic gadgets also. The electronic gadgets now become very compact. Okay, so we will discuss what are the consequences of reducing the device dimension. By device, I usually mean MOSFET, that is metal oxide semiconductor field effect transistor. So we have, over the years, we have been reducing the size of the MOSFET. So we will discuss what are the consequences of that. That is known as a scaling effect. Okay, and how those effects can be removed, or even if even if we can't remove those effects, how we can improve its performance, okay, while maintaining or reducing the reducing those effects. Okay, we'll discuss limitation of conventional device and so on. Now, as this is a nano structured device or device is in the nano regime, often a classical explanation will not be that useful. So we need to understand bit of quantum mechanics. Okay, so we will cover little bit of quantum mechanics, not in much detail. We will talk about bit of quantum well, quantum wire, quantum dot, this kind of structure. We will be discuss bit of density of states. Okay, we will discuss bit of photoelectric effect. This is a class 12 thing. Okay, so this is very easy, but we will discuss that a little bit because that is the starting point of quantum mechanics. Then we'll discuss bit of wave particle duality, Schrodinger equation, and so on. So this is very preliminary or basics, and maybe you know these things beforehand. Okay, but still I prefer to cover that part. Then we'll talk about little bit of carrier transport, okay, of these quantum structures. Then we will move to some advanced semiconductor devices. Okay, for example, we'll talk about tunnel FET, we'll talk about FinFET, we'll talk about um, HBT, we'll talk about MOSFET or HEMT, that is highly mobilized or mobility, high mobility devices. Okay, so these are advanced devices that we will like to cover. If we get time, we will cover a little bit of laser, quantum cascaded laser, for example. We'll talk about single electron transistor. So you see, lot of devices we will cover. Okay, lot of devices, because it is quantum electronics. So we will cover a lot of devices. Then we will cover as we want to develop very tiny device, then lithography is very important. So we'll talk about not only optical lithography, which is basically conventional lithography. We'll talk about different kinds of lithography which will help us to fabricate such tiny devices. For example, double pattern lithography we'll discuss. Okay, then we will cover bit of characterization techniques, because as nanostructures are very tiny, it is not possible to see them over with naked eye, not even with optical microscope, because in optical microscope our visible range is, you see, around 400 to 700 nanometer, whereas as I told you, the nanostructures or nano materials or the one we know as nano or we discuss as nano is around say 100 nanometer or less than 100 nanometer. So we need to need some special kinds of characterization tools. So if we get time, we will discuss briefly some of these characterization tools. For example, atomic force microscopy, scanning electron microscopy, XRD, XPS, TEM, UVVs, and so on. So these are very basics. We will just touch upon those. Okay, and at the end, again, if time permits, we will talk about not only silicon, because whatever discussion we are going to have based on silicon, gallium arsenide, all these devices are made on using those material. But at the end, we will give you some perspective where we will discuss other materials. Those are non-silicon materials. For example, MOS2, WS2, HBN, graphene oxide, okay, carbon nanotube, etc. Again, very briefly, just to give you idea that how the research and industry is progressing as far as the nano electronics is concerned. So there are two aspects. One aspect is using conventional silicon or gallium arsenide. We are reducing the dimension of your devices, okay, and try to reach in the nano regime. There are a lot of advantages if we can do that, and that is what we have been trying and what we have been doing in last 4 decades or so. But the thing is, often we faced a lot of challenges, and then we thought that silicon will not go much further. So people started trying other materials, for example, carbon nanotube, graphene, MOS2, WS2, HBN, and so on. So these materials, they have some advantages which is over that of silicon. Okay. And then again, on in the way we managed to overcome the hurdle with silicon and we move on, because the industry prefers silicon for various reasons, and all these other materials, that carbon nanotube, graphene, and all that, these are still in the research domain. Okay, very few industries actively participating in developing devices using these non-silicon materials. The industry likes silicon, and we have very matured microelectronics or nanoelectronics technology to fabricate device using silicon or 3,5 semiconductor and so on. Okay, but we don't have the technology is not that mature when we talk about carbon nanotube, graphene, and all that non-silicon material, right? So we will discuss those perspective and give you some overview about how the industry are progressing and how the research and development is progressing. So this non-silicon activity is still in the research domain. Various universities involved, of course various industries also involved, that they have been pumping lot of money in this research, but they are not actively participating in it, in a sense ki they are not developing the, devices using these, because they will pitch in when the they will see more into it. Okay, they will see more opportunity into it, but for the last 10-15 years, all this non-silicon based material or devices based on this non-silicon material is still in the research domain, right? So this is tentatively the syllabus. As I mentioned, uh, we'll try to move slowly, and in fact in other years also I don't finish, or I couldn't finish the entire thing, but what I do, I try to give you glimpses of different aspects. For example, if you look carefully this particular syllabus, there are roughly four aspects. Let me So one aspect is a device aspect. So we'll talk about short channel effect, advanced devices, and so on. So this is one aspect. Okay, so how these devices are performing, in which direction the nanoelectronics is heading. So this is one aspect which we are going to discuss in greater detail. There is another aspect which is quantum mechanics. This quantum mechanics, as I mentioned, we will discuss briefly and very basics, so that whatever discussion we will have here will make sense using this quantum mechanics. Because as I said already to you, with classical mechanics, some of the things is difficult to explain in this nano domain, right? So we will learn quantum mechanics briefly, and as I apprehend that probably, as I guess that probably you know these things, but we'll just brush up those quantum mechanics knowledge. Then there is another aspect which is lithography or fabrication, how we fabricate such devices. So we will discuss very briefly. We will discuss little bit of optical lithography, e-beam lithography, and then we will move to double pattern lithography. With this double pattern lithography, you manage to get or you manage to make very tiny devices. Okay, we'll talk about little bit of nanomaterial synthesis, how nanomaterial can be made, and so on. Okay, and also nanostructure characterization. So these are the four aspects, okay, which we will try to touch upon. Not necessarily we will cover everything, or we'll be able to cover everything in next 4 months or so, but what we will do, we will try to touch all of these, so that we get some idea about nanoelectronics. Okay, now if you ask me books, there are several books, but still I mean, it's difficult to get, as you see the syllabus, it is difficult to um, get all the things from the same book. So say there are several books. I will when we go through any particular thing, I will mention, or I will try to mention from which book I am covering. Sometimes you can have things from the net itself. Sometimes you can have things from the published papers. Okay, there are some recent papers, some very iconic papers, for example Moore's paper and all that, Donat's paper and so on. So we will cover things from various avenues. For example, like, Streetman's book, Z's book, these are very classical books. Okay, where they discuss some aspects of those advanced devices which I mentioned, like HEMT, HBT, FinFET, and so on. Okay, this is a book which covers bit of characterization, bit of nanomaterial synthesis, and so on, bit of quantum mechanics. Okay, and so on. There is a book written by Professor Bhatt from ISC, Fundamentals of Electronic Devices. You can see that. So as long as whatever book you like, you can just go through it. As long as it is covering whatever we are discussing in the class, that will do. Okay. Um, so that's about book. Okay, we'll time to time I will try to share some of the journal papers which you can, or conference papers which you can go through it, try to understand things in a much better way. Okay, now, and this is a old slide when we had like face to face discussion, physical classes. I used to have this kind of benchmark. So 30 marks like for mid sem, 50 marks is for end sem, and 20 marks as teachers teachers prerogative. This is like among these 20 there was like class test 1, class test 2, attendance 5, and so on. So this was the old slide when we had like physical classes. I have to see how it goes, but there will be definitely marks on attendance, say 5 marks on attendance, and maybe 15 marks on maybe some quiz. Okay, quiz in Moodle, that we will see how it goes. Okay, so that way we might cover 20. So here maybe 15 on quiz. Okay, at the end of the semester, and attendance maybe 5 marks, so that way 20. And this we will see how maybe 3 exam I will try to take. Okay, I will see how it goes. Okay, but I will at least 1 week or 10 days before I will tell you that okay, we will have one exam now. Okay, so at least 1 week before, 10 days before, I will give you I will tell you that we will have exam. But so please go through things whatever will be covered in the class, without waiting for the exam, because we will have like I'm thinking about 3 exam, but we'll see how it goes. So there will be exams, so you please prepare for that, and go through stuffs. Now this is a slide just to show you, just to give you some idea about nanostructure. For example, our human hair typical dimension is few tens of micrometer. Okay, few tens of micrometer is our human hair. Our red blood cell is around like few micrometers. Okay, whereas when we talk about our nanostructures or nanostructure based electronic devices, they are very tiny, as I told you before, like around 100 nanometer or so, or less than 100 nanometer. For example, this is an ACM image. ACM I mentioned to you, scanning electron microscope. That is a characterization technique through which we can see the nanostructure. ACM image of carbon nanotube. Okay, of diameter around 50 nanometer. Okay, and so on. So this is like forest of carbon nanotubes. Okay, this is they tried to write the name of a college, Peter House, with carbon nanotube, and using lithography they managed to have like carbon nanotube in a very specific places, and so on. So these are just few examples of how the nano structure or nanomaterial looks like. Okay. So I think that's about it in the syllabus section. Do you have any queries? Do you have any queries? Then could you please raise your hand, and then we can uh, uh, if you have any doubt, any queries, please raise your hand, or any comments. Am I going very fast, very slow? Whatever we have discussed is understandable or not? Are you happy with whatever we have discussed? No comments. Okay. In my ERP, I have just seen 9-10 of you, but here you are 20 odd students. Why there is a difference? You haven't done the registration?
Yes, sir, I have not done.
Okay, okay. So most of you are MTech first year, or there are BTech students also? Okay, I'm assuming most of you are MTech students. So you have any comments about the syllabus, or any part you are you want me to elaborate, or anything you want to um, you want me to go there again, discuss things, or you are okay? Okay, so uh, let's start. If I go back to my uh, so this is from where we will start. Okay. uh, uh, Shrinking of device dimensions. Okay, this is from where we will start. Um but before we start, can we have a small introduction part, because I can't see you and I don't know who you are. So is it possible, just uh, next 5-10 minutes, could you please introduce yourself? If possible, you can switch on your camera momentarily if network permits. Aditi, could you please start? Aditi, if I go alphabetically, Aditi Gupta.
Yes, sir.
Yeah. So could you please introduce yourself very briefly, and if possible, switching your video on.
Yes, sir. Sir, yes, sir. Hello.
Yes, Aditi, go ahead.
Hello.
Yeah,
Yes, sir.
I can hear you. Yeah, I can hear you.
Yes, sir. Sir, actually, there is some network issue, so I am hearing
Right.
voice.
You don't
I am
have to
hearing
switch on the
video.
video. Could you please introduce yourself a little bit? Are you MTech student?
Yes, sir. Yes, sir. Sir, I am a tech student
Yeah.
and I am from Kanpur.
Right. And you did BTech from where?
Yes.
You did
Yes.
BTech from where?
Yes, sir. Sir, I did BTech from Institute of Engineering and Technology, Lucknow.
Okay. Um, Oiranti Mina?
Hello, sir.
Yeah.
Good morning, sir. I am Eranti Meena. I completed BTech from Government Engineering College, Ajmer, and now I am MTech first year student.
You are MTech in EC, right?
Yes, sir.
Okay. Okay. Alex?
Thank you, sir.
Thank you.
Sir,
Yeah.
I'm Matthew. I'm from Kerala. I did my BTech from RCT in Kerala. I am a student of microeconomics in VLSI.
Okay. Okay. Ambuj? Ambuj?
Uttar Pradesh.
Ambuj, please go ahead. No, I can't hear anything. I can't hear you.
Hello, sir.
Yeah, yeah. You're audible now.
Sir, sir, I am Ambu Shukla
Right.
from Prayagraj, Uttar Pradesh. I have done my BTech from JECRC Jaipur and I am
Right.
an MTech student.
Okay. Amit?
Hello, sir.
Amit, yeah.
Sir, my name is Amit Kulshrestha. I am from Jhansi, Uttar Pradesh. I did my BTech from BIET Jhansi, and I am a MTech student from Microelectronics VLSI department. Bangalore.
Right. Thank you. Orijit?
Good afternoon, sir. My name is
Yeah.
Arjit Dubey. I
Right.
completed my Bachelor's of Engineering from Jabalpur Engineering College, Jabalpur, MP. And I am from Hoshangabad, MP. And I am enrolled in MTech course.
Right. Ayush? Ayush? Yeah. I think you are muted. You are muted.
Good morning, sir.
Good morning.
I did my BTech from IET Lucknow and I am from Gorakhpur. I am MTech first year student.
Okay, great. Okay. Thank you. Balakrishna?
Good afternoon, sir. Sir, am I audible?
Yeah, yeah, yeah. Good afternoon. Yeah.
Sir, I am squad leader Balu Krishna. Sir, I am a sponsored candidate from Indian Air Force. Right now, I am posted to Air Force Station Kalaikunda, and I completed my BTech from Kochi University of Science and Technology in 2010 from EC.
Okay. Okay. Excellent. Okay. Thank you.
Okay.
Then Shurendra?
Good afternoon, sir.
Good afternoon.
I am from Andhra Pradesh, sir. I completed my BTech from JNTU Anantapur, Andhra Pradesh,
Right.
and I am enrolled in MTech VLS.
Okay. Great. Great. Then Dinesh?
Hello, yes, sir. I am Dinesh Kumar from Patna, Bihar. I have done my from Technoden Satellite, Kolkata, and I am
Right. Okay. Your voice is a bit cracking. Probably network issue is there. Okay. Anyway, thank you. Divang?
Yes, sir. Good afternoon,
Yeah.
sir. My Ram Kumar Singh
Right.
from Engineering Tech. Right now, I'm in.
No, your voice is also cracking. It's not audible. Mm, maybe again some network issue is there. Um, okay. Okay. We will probably move on. Dunga, could you please introduce Dunga
Good
Bharat?
afternoon, sir.
Yeah. Yeah.
So my name is Bharat Kumar. I have completed
Right.
my BTech from Pune, Army Institute of Technology, Pune, and I am from Andhra Pradesh, and I have enrolled for MTech course.
Right. Okay. Excellent. Gaurav?
Good morning, sir. My name is Gaurav Kumar from
Yeah.
Bihar. I have done my BTech from Gyanendra Singh College of Engineering, Bathinda. I have enrolled MVLSI course.
Okay. Thank you. Govind?
Good afternoon, sir. So my name is Govind Sharma, and I am from Ghaziabad, Uttar Pradesh. I had completed my BTech from ABES Engineering College, Ghaziabad, Uttar Pradesh. Presently, I am enrolled in MTech course.
Okay. Okay. So then Gurmeet? Gurmeet? Gurmeet
Hello,
Kaur
am I
Arora?
audible?
Yeah. Yeah.
Yeah.
Please go
Good
ahead.
afternoon, sir. My name is
Yeah.
Gurmeet Kaur Arora. I am from
Right.
Indore, Madhya Pradesh. I have
Mhm.
completed my bachelor's of engineering from Government Engineering College, Ujjain, and currently I am MTech student.
Right. Tausif Rahman? Good afternoon. Right. Right. Oh, I can remember you. I have taken your interview. Okay. Good. Good. Yeah. So Mukul?
Hello, sir.
Yeah.
My name is Mukul Gupta. I am from Chandigarh. I have done my BTech from UIT Chandigarh. I am a MTech student.
Good. Nalapati Pawan Kallan?
Good afternoon, sir. I am Pawan. I have done my BTech from ISM Dhanbad, and I am MTech microelectronics student, sir.
Right. Good. Nilesh?
Yes, sir. Good afternoon, sir. My name is Nilesh Kumar Sahu. I am from SUNY Madhya Pradesh. I did my BTech from Jabalpur Engineering College, and currently I am MTech student in microelectronics and VLSI.
Right. Nitesh? Nitesh Rai?
Good afternoon, sir. Myself
Good
Nitish
afternoon.
Rai. I'm from Ayodhya. I did my BTech from NIT Patna, and I am first year MTech student in EC department.
Right. Penapati Sudhir?
Good afternoon, sir.
Penapati
This is-
yeah.
I am from Amalapuram, Andhra Pradesh, and
Right.
I am a final year dual degree student at IIT
Right.
Kharagpur, sir.
Okay, final dual degree student. Okay, great.
My BTech from Rajasthan Technical University, Kota, and I am MTech first year student.
Right. Pujita?
Good afternoon, sir. I'm Pujita. I'm from Andhra Pradesh, and I'm an MTech student, and I have done from my BTech from Gayatri College, Visakhapatnam, Andhra Pradesh.
Right. Priyank? Priyank Bharadwaj?
Good morning, sir. I am MTech student, first year. I am from Ghaziabad, Uttar Pradesh, and I did my BTech from Gautam Buddha Technical University.
Right. Okay. Sanjeev Krishnan?
Good afternoon, sir. I am Sanjeev Krishnan. I am from Kanyakumari, Tamil Nadu. I have done my BTech from College of Engineering, Trivandrum, and I am currently in my first year MTech in signal processing, instrumentation and signal processing.
Right. Okay, so Saurabh Gopal?
Good afternoon, sir. My name is Saurabh Anzhade. I am from Maharashtra. I have completed my BTech from Government College of Engineering, Amravati. Currently, I am enrolled in microelectronics and VLSI MTech first year.
Right. Savannah? Savannah?
Good afternoon, sir.
Yeah.
I am Madhuri. I am from Andhra Pradesh. I have done my BTech in Guru Ghazidas University, Bilaspur. Currently, I am pursuing MTech in microelectronics and VLSI. Thank you.
Right. Okay, thank you. So did I miss anyone?
Sir, I have missed me, sir.
Krishnakant.
Okay, please go ahead.
Good afternoon, sir. This is Krishnakant, and I am from Telangana. I have completed
Right.
my BTech in JNT College, Hyderabad. Currently, I am an MTech student in microelectronics and VLSI.
Okay, great. So anyone else? Okay, so my name is Prashanta Kumar Guho. So my name is Prashanta Kumar Guho. I joined. My background is electronics. I joined in the EC department 2010 September. So since 2010, I've been here. End of 2010. I'm the associate professor now. So my area of, I mean, the courses I offered or I take is one of the courses nano electronics. I used to take another course is VLSI technology, that is the fabrication processes of semiconductor devices. So that is VLSI technology. So I used to take VLSI technology in other semester. So apart from nano electronics, now I am taking a basic electronics course. That is another course for all the students, common students, undergraduate students. So basic electronics course is offered by EC department for the whole IIT for different departments. Okay, so that course also I take. So yeah, so nano electronics, VLSI technology, basic electronics or introduction to electronics, etc. These type of courses I have been taking. Now my research area is sensors. I work mostly on gas sensor, MEMS based gas sensor. But I use nanomaterial to make those gas sensors. So that is my area of expertise. So yeah, so that's about me. It is not great that we can't meet face to face, but the situation is like this. So what I will do that I will try to upload my notes in the MS Team, and board work in the MS Team. Okay, so if I do some board work, I will upload it in the MS Team. I think video will be automatically uploaded, but the class notes and the board work I will upload in the MS Team. More or less regular basis, but if I miss it, you please remind me in the next class, then I will upload it. Okay. If you don't know my email ID, you should be able to find it. Find the email ID from. Let me write it here. This is my email ID, pkguho@ec.iitkgp.ac.in. If you want to contact with me, you can drop me an email. Don't expect to get reply all the times, but I will try to be regular. Okay. So this is the topic through which we will start today. We have sort of 15-20 minutes left in this class, but let me so this is some introduction part, and also this will give you some perspective in which direction nanoelectronics is progressing. Okay, so I think today's 15-20 minutes and probably next Monday entire 2 hours we will spend on this particular aspect, that is IC roadmap, that is integrated circuit roadmap, in which direction nanoelectronics is progressing. This we will discuss. This will cover the scaling effect and all that, how we have overcome different challenges while we reduce the dimension of our semiconductor devices. All this we will discuss in this particular topic, so it will be it will go up to next week, I think. Okay, so so this, as I mentioned to you a little bit earlier, that not only silicon, there are other materials which also people have been venturing, particularly universities, research institutes, etc. The reason they are venturing in those domain as well, because sometimes those material has advantages over that of conventional silicon, right? So and even if we make materials which is not with silicon, then we can't. So there are two aspects, two places from where we fabricate our device. One place is our universities, our research labs. Okay, that is one place, and another place is industry. Now, if you want to make an IC, integrated circuit, that is basically using CMOS, then it has to be from industry, because you can't make in your lab. You can't make, for example, a processor, Pentium processor. You can't fabricate in your lab. Okay, but not even Pentium processor. You can't fabricate an op-amp which contains maybe 15, 20, 30 transistor in your lab. It is not possible. Okay, so what you can do, you can make some advanced devices, you can make discrete devices. Okay, usually batch fabricated or hundreds of thousands of devices, it is not easy to make. Okay, so people who try to, what I want to say is, if you want to fabricate your circuit, okay, you have to use the facilities, industry facilities. For example, there are many fabrication foundry, for example, the TSMC, UMC, XFab, Global Foundry, okay, AMS, and so on and so forth. There are several foundries. Okay, unfortunately there are none in India. I mean, there is one or two, but those are not great. But probably you have heard recently the government has announced they want to develop this fabrication facility in India also. But anyway, what I want to point out is, like, if you want to fabricate your integrated circuit, okay, then you have to fabricate it in the commercial foundry. You can't do it in your university. I mean, even not only in IIT Kharagpur, it is not possible even in MIT also, right? So there is no point in making integrated circuit of 100, 200 transistor in your lab. It is not possible. It doesn't make any sense. So that is one aspect. Another aspect is, if you want to do a lot of futuristic research, for example, if you want to develop a single electron transistor, or you want to venture on non-silicon based material, graphene or MOS2 and so on, and try to develop a device which might have future potential, so that they can be made, if they are good, they can be made in thousands or in lakhs, in millions, etc. Okay, so when they will be made in thousands or in 10,000 or in millions, that will be done in the fabrication foundry. Okay, commercial fabrication foundry. But initial research for those needs to be done in-house. Okay, so that is, so what I want to point out, if you want to make discrete devices, if you want to make devices which are like futuristic, those TSMC or AMS or Global Foundry, they will not venture money on those, or they will not spend time on those. Okay, they probably give you money to fund your project if they think that it has some future potential. But that type of single or few devices you have to do in-house, or you have to fabricate in-house. So fabrication takes place in two parts. One is in your own research lab, in your own university, or in your own research institute. Okay, but when you have like batch fabrication, you want to have like millions of devices on your chip, that has to be done by a commercial foundry. This is not only true for the universities also. This is also true for many companies. There are thousands and thousands companies out there, semiconductor companies, who design their circuit, but they fabricate it using commercial foundry. It is not possible. Though all these companies are fabless, okay, they design their circuits and things using cadence or mentographics or synopsys, etc. But then they fabricate it from commercial foundry. So these are the two aspects. Okay, now as we will discuss or we have been developing lot of nano structures, okay, or maybe nano sensors, or maybe MEMS based devices, that you need to integrate it, okay, that you need to integrate it so that you can get the advantage of integrated circuit or circuits so circuits is you send it, you design it and send it to the commercial foundry, but later on you have to integrate your nano MEMS based devices or sensors, which is not made by these commercial foundries. These are like usually made in-house. MEMS based devices is made commercial foundry, that is a separate foundry. This is not CMOS foundry, but your sensors and nanostructures you make it in-house, and then you have to integrate it with your integrated circuit. Okay, so these aspects, these are the IC roadmap we will discuss in our in this class. Okay, now this is a typical schematic of a wafer, of a silicon wafer or a CMOS wafer. By CMOS I mean if you manage to make both PMOS and NMOS on the same silicon die, that is basically CMOS, right? Now this wafer usually contains this is the conventional layers. Okay, so these usually contains silicon. So this ash color one is color block is basically silicon, and also this block is also basically silicon. Maybe this is a well or some other doped region and so on and so forth. So there are other, apart from silicon, in your integrated circuit there will be other materials available. What are those? For example, you can have polysilicon. Okay, for example, gate is made of MOSFET gate is made of polysilicon. Okay, so there might be one polylayer or multiple polylayer. Okay, so polysilicon you can use as a gate on top of gate oxide. There usually a polysilicon layer. Okay, so for example here and here. So this also polysilicon can be used for other purposes. For example, we can have a capacitor using polysilicon. We can have like a resistor using polysilicon. Okay. Now then there are several metal layers. For example, you see metal 1, metal 2, metal 3, metal 4, and so on. There may be 7, 8 metal layers depending on which kind of process, CMOS process you are using. Okay, and these metal layers you see separated by oxide. Okay, you see oxides. Okay, otherwise these metals will be shorted, right? So you need insulating layer to isolate individual metal layers. Okay, so there are multiple metal layers, and on top of the top metal layer, maybe say in this particular case metal 4 is the top metal layer, say maybe it is a 4 metal layer process. Okay, and then there will be oxide and nitride, silicon nitride. So these are passivation layers. So this layer is used to cover the entire chip so that the chip remain intact. Okay, your circuits remain intact. So this passivation layer is at the top, is usually made of oxide and nitride, and the reason we need several metal layers so that we can reduce the footprint. Okay, I don't know how to. So this is a side view. This is a side view. Now if I want to look at the top view, which will help me to understand why we need so many metal layers, say I have a top view like this. So top view of my chip is this. Okay, and there are different maybe hundreds of devices, MOSFET, resistor, capacitor, and so on. Several hundreds of MOSFETs are there, right? To make your circuit. Maybe you are making making an ASIC chip, okay, application specific chip, or something. Maybe you are making an op amp or whatever. So these are many devices, okay, in the chip, and you have circuit. You have to have metal connections, okay, so that these devices can be connected, right? Now what happens is, like, if we have only one metal layer, metal 1, okay, then what will happen, these connections between different devices will take lot of space, because you have only one metal layer, and say I am connecting this point and this point, okay, and I say I need to connect from here to here, then you have to go all the way like this, okay, right? Say I have to connect from here to here, then you have to go all the way like this, right? So that is very difficult, and that will increase the size of your circuit. But say if I have a different situation means I not only I have only one metal, I have several metal layers, okay. Say I have two metal layers, for example. So what I can do, I can from here to here, okay, without going in this direction, what I can do, I can go like this, and then I will have like metal 2, okay. So let me just change the color so that it is where is the color, yeah, color, okay. So say this is metal 2, so metal 1, then metal 2, then metal 2 to metal 1 again, okay, or maybe you go all the way here so that you can cross these two metal 1 lines, and then from there you you connect this. So you see, instead of going all the way like this, you can make things very compact, okay. So this is just two metal I'm talking about. If you have more and more metal layers, you can make things more compact, okay. Your footprint going to reduce, okay. So what we are doing, we are like making flats. In case instead of making houses, individual houses, if we make flats, then we have like families on top of one another, okay. There are houses on top of one another. So we are using basically the third dimension. Here also we are using the third dimension, okay, without sacrificing the footprint, right? So we'll be able to reduce the dimension of your system if we have like multiple metal layers. I hope that is clear to you. So that is why we have like several metal layers in a conventional CMOS process. Those layers will be isolated by oxide, but wherever you need to connect them, you use via. For example, this is called via. So this metal 1 and metal 2 is connected here. This metal 2 and metal 3 is connected here. So this, as I said, here it is metal 1 and metal 2, here it is connected. Here also metal 1 and metal 2 is connected, okay. So this connection, when you are making this connection, you remove oxide from that place, from here, and you connect metal 1 and metal 2. You remove oxide and connect metal 2 and metal 3, and so on. These are known as via or via, okay. So these vias are useful to connect them wherever you need, and wherever you don't need, you just isolate them using oxide, right? And as I said, at the top there will be oxide layer and nitride layer, which will act as a passivation layer. So this is a typical CMOS wafer, and you know, this is like NMOS, and this is like PMOS, okay. Say this is a p-type substrate, and then it is N-well to make PMOS, and directly on the p-type substrate you can make your NMOS, okay. And this is the substrate contacts here, this is substrate contacts here. So this is a typical CMOS structure. This is NMOS side and this is the PMOS side, right? So here I will stop today. if you have any doubts, you can just, we have probably 5 minutes, so you can just ask me, otherwise we'll take from here. You have any doubt, you can raise your hand, and then we can discuss if you have doubts. No doubt? I mean, my pace is okay, or I'm just going very fast?
Sir, I have one doubt. Sir.
Yeah, please go ahead.
Sir, my question is, are all the metal layers identical in weight, in size, or they are different?
I mean, no, metal width may be identical. So let's put it this way: the size of the metal layer depends on you, depends on the designer. Okay, because the length of the metal layer and width of the metal layer on you, there is a flexibility. So so if you make wider metal layer, if you have like a lot of current, some metal track might carry lot of current, say some power line or ground line, so you have to make that metal track wider. Okay, again, the length depends on the distance between the devices from where to where you are connecting. So the designer I mean, they give the facility to the designer that you can choose your length and width of the metal track, so that's not an issue. But the thickness of the metal track is the foundry specified. You can't change thickness of the metal track. Is that your question?
Yes, sir. Yes.
Right, but these metals depends on the processes. It used to be made with aluminium. Nowadays, these metal layers are made of copper. Okay, vias is made of different. Some is made of copper. Nowadays, people are trying carbon nanotube in vias and so on. But usually, it is made of copper. But thickness between different metal layer varies. Okay, it depends on various things. Let's not go into that. But thickness is not in our hand. Thickness is driven by the foundry. In fact, all the thicknesses which I have shown, I mean all the layers which I have shown, silicon, then polysilicon, oxide layer, all this thickness is not in our hand. Thickness, resistivity, material property is not in the hand of the designer. The circuit designer will just design the circuit and it will be fabricated. Circuit designer can change the width and length, but not the thickness, not the doping concentration. Okay, so these can't be changed. Right.
Thank you,
Anything
sir.
else? Anything else? Okay, so great. So we will meet on Monday, 8 a.m. Okay, and I'm not going to upload. I will upload the syllabus thing. I'm not going to upload this second thing we have started because we have just gone through 1-2 slides. So let me cover it on Monday. Then we will upload it. Okay. So thank you very much and thanks for joining the class. Okay, great day.
Thank you, sir.
Thank you.